With this module, we're going to return to our consideration of thermodynamics, and that means we're going to get back into the business of work, heat, internal energy, and enthalpy. But in particular, we're going to move toward defining some new thermodynamic quantities that are going to become very useful. But before I do that, I need to basically take care of some old business and clear up some ideas about reversible and irreversible processes. And I want to do this by focusing on work and how it can differ between a reversible and irreversible process. Now, in this case, we're of course going to be talking about expansion and compression and how those are affected by whether or not a process happens to be reversible or irreversible. Now, the way I'm going to do this is I'm going to consider some systems in which I have a gas that's confined to a piston. And so I'm going to draw my piston here. And I'm going to actually make this sort of a closed off piston, so it's an artificial piston, if you will. But it will have a piston head here that will separate the system, which will be in the lower half, from the surroundings, which will be in the upper half. So let's just say that these surroundings are something that I can adjust externally to the system, and the system is going to be this part down here. Okay, now one of the things that we will, and I'm going to put system gas in here. Okay, this is a gas that can expand or can contract. Now, one of the things that we can do to control how fast this expands or contracts is to put a dish up here, and this dish will contain some amount of water or some other fluid that we can put into there, and by adding or decreasing the amount of water in there, we can add or subtract to the weight, and therefore we're going to affect the pressure that is exerted on our system down here externally. Now, the whole idea here is that we're looking at the notion that a change in work is going to be equal to pressure over multiplying by a change in volume. And the thing that we want to control here is, what is this pressure? Now, let me tell you why I'm worried about this. For example, if I'm doing a reversible process, well, no, let me just, any general process of work, I'm going to have a certain pressure that I'll call pressure internal that relates to the gas that's in the system. So when I'm talking about an expansion, the only way I can get this gas to expand is if somehow the external pressure is less than the internal pressure. So in other words, the internal pressure is greater, it can push out, it can make that expand. Now, if this were true, this would basically be an irreversible process, because there's no way I could stop the expansion of the gas from pushing against a lighter external pressure. So in this case, we will always have external pressure. If it's less than the internal pressure, then the work that we're doing, that we're expressing in this statement here, is really a work that is being performed against the external pressure. So you see here, by having the external pressure less than the internal pressure, it's basically determining how I'm going to be calculating this work. Now, I could do a similar thing for a compression, and if I did that, in that case, I would need to have my internal pressure be less than my external pressure. So in other words, this would have to be the case. And this again would be an irreversible process, because the external pressure, I can't stop it from basically pushing down and compressing the gas inside the piston. But in this case now, the work is being done against that internal pressure. So in effect, the work is always being done against the lesser of the two pressures. Now, I could also do a change in this work that is somehow due to a case where I'm going to control the water that's placed on top of this piston, and control it in such a way where I have the internal pressure is always equal to the external pressure. And so if I want to compress the gas, I would slowly add water to the container up on top of the piston. If I wanted to slowly expand this, I would slowly take the water out. All right, in effect, what we're doing is we're maintaining an equilibrium between the system and the surroundings. And we're doing that by keeping these pressures very close to the same. And we can change those pressures incrementally, and that will allow the system to either slowly compress or slowly expand. When we do this, this is what is giving rise to a reversible process. So in other words, a reversible process is one that is essentially at equilibrium, and it involves a slow change, either an expansion or a compression, as we move along. Now let me show you on a PV diagram sort of what this might look like. So here's our PV diagram. And just for the sake of convenience, I'm going to assume that all of these processes are being carried out isothermally. So in other words, we're maintaining a constant temperature as this goes. So that means that we're going to have an isotherm, and our initial and final points are going to be located on that same isotherm. Now let's look at compression first. Okay, what has to happen in order for compression to occur? Well, what I'm drawing on the PV diagram is actually the system coordinates. So I'm showing you what the system pressure is and what the system volume is. And that doesn't tell me anything about the external pressure. So in effect, what I'm saying is that if I have an irreversible process, I can't actually adequately represent that on this PV diagram unless I cheat a little bit. So I'm going to cheat a little bit. Yep, let's get rid of that. And the way I'm going to cheat is to say, okay, let's say I'm starting here and I want to compress the gas. That means I'm going to increase the effective external pressure to somewhere up here. So now when I let go of this piston and let it proceed spontaneously, it will compress over to my final point that's listed over here. So you can see that what I'm doing here is I'm generating a process where I'm artificially changing the pressure that's external so that I can actually compress this gas, and it's an irreversible process. However, the work that's involved here, let me just draw this down as the work is basically going to be the area underneath this curve. So it's all of this. That's the work involved in the isothermal irreversible compression. All right, if I had been doing this in a reversible way, however, then I would have stayed on the isotherm. So in that case, I would have looked at a process where I'm starting here and I'm ending here. And I'm going to stay on this isotherm, and I'm basically going to do that by doing a bunch of little tiny microscopic steps that go along this. And at each step, I'm maintaining the equilibrium between the external environment and the internal environment. So when I do that now, the work that I'm going to generate in doing this compression is here. And we can see, I think, visually that the work of the reversible process is less than the work of the irreversible process in this particular case, in the case of compression. Now it turns out, and I hope this would be evident, but I'll draw a picture just to make sure that it is. If I'm doing expansion, I'm going to have the opposite. So here's my isotherm, and now I'm going to start up here and I'm going to end down here. And if I'm doing this using an irreversible process, I need to reduce the external pressure down to some lower quantity. So this is the external pressure here, so that when I let go of the piston, it will expand to come out to the final pressure here, which is my system pressure. So this is my P internal now. All right, when I do this, the amount of work that I'm actually generating, and in this case the system is doing work on the surroundings, so the amount of work that I'm generating is down here, whereas for an irreversible process, again, I would be doing incremental changes along the isotherm, so the work would also include the area up here. So I think it's clear to see for the reversible process in this case, it's going to be greater than the irreversible process, and this is for expansion. All right, so this was basically a little primer to help you understand kind of the fundamental difference between reversible and irreversible work. The reversible work is taking place at equilibrium, and it represents an extreme value. I cannot generate more work for an expansion than the reversible amount. So this is the maximum. Likewise, for a compression, I can't generate less work than the reversible amount of work. And this is going to come into play now when we begin to talk about changes in the heat, as we'll see in the subsequent videos.